today is outdoor high voltage insulators. Now, when we take a look at high voltage insulators, the first question we ask is, now this insulator, what is this insulator and what is it for? Well, if you take a look here, we have quite a few power lines running here. And just for yourself, answer yourself, is this an AC or a DC line? And this obviously is 3 phases AC. And if you take a look here, we've got the 2 polar for the DC line, the 2 poles, and then the earth and the shielding. Okay. Now, if you take a look further, you will see that these power lines are suspended from a structure, and they suspended from the structure with something we call an insulator. Now, that insulator that is sitting there is there for a very, very good purpose, because it has to insulate this high voltage, because these conductors are at high voltage, and in this case, most probably 600 or 800, most probably 600 kV, yeah, DC, and this has to be insulated from ground potential, because the structure here is at ground potential with good tower footing resistances, and the structure is mechanically designed to be able to take the weight and all the various stresses which is put onto the structure by this conductor being suspended from the insulators from the actual tower structure. Now, this insulator needs to insulate this high voltage from ground potential. Then at the same time, it must be able to withstand, okay, a lightning induced overvoltage, a switching overduced in voltage, a lightning striking the tower, raising the tower potential, backflash over voltage potential, okay? So this poor insulator has to be able to handle a lot of electrical stresses. Then at the same time, this insulator is mechanically stressed, because you find that with these long catenaries, these long spans, that the wind pushes against the span, and then that wind loading also puts mechanical loading. The weight puts loading onto this insulator. So there's a lot of mechanical stresses. There's vibrations which take place in this conductor, which also then at the end of the day is transferred to all these fittings and all the hardware down on the live side. And you will see that from the electrical side, we have to reduce the stresses by putting on corona rings to reduce the electrical stresses. And this insulator then, it's not in a clean environment. We got the wind, we got the rain, we got the lightning. We can have birds sitting up here excreting into the gap, causing an air flashover process. We got the birds excreting onto the insulators, which can cause pollution problems. We then have airborne pollution particles coming around and polluting these insulators, and basically changing the resistance on the layer of the insulator to such an extent that when you get enough wetting, electrolyte forms, the insulator flashes over. Oh my goodness. Insulator is not just an insulator. An insulator is quite a critical element, because if that insulator had to fail mechanically, this line drops. If the insulator fails electrically, you can't transfer the energy, because you've got something taking the energy down to ground at the tower structure. So this insulator is a very critical component of this whole line and the line's functions. The same in the substation. All voltage levels, all the way right down, your insulator plays a critical role. And without addressing all the issues which those insulators are subjected to, and not selecting the correct insulator, you could have an extremely poor performing transmission, distribution, or reticulation network, which is terrible. These insulators, obviously, they are used in different configurations, like I, V, I configurations. And yeah, we got double V here. And then you got, they also tension. So this is suspending the suspension insulator. Then you got the insulator where you got one on this side, one on that side, with a jumper in between, and that is then taking strain from the conductor. This is suspending the conductor. There's a lot of different terminologies associated with the insulator, and hopefully today I will be able to take you through very, very, very few components of it, because I normally lecture a full week just on high voltage insulators, and we've got 2 different courses I do on high voltage insulators. So having 2 hours to your disposal to inform you guys about everything of insulators is not possible, but I can at least expose you to the basics. Now, what it's all about in these insulators, it is to achieve a balance. You need to balance up these different aspects with one another. So you need to take a look at what the insulator is subjected to electrically, mechanically, the climate, the actual physical size and the handling and so on of the insulator, and then you take those external stresses which the insulator is subjected to handling. The majority of damage to insulators today is due to poor handling, transportation, and installation practices. The guys damage the insulator before it is actually even energized. So there is one of our biggest external stresses, is just the scenario of handling it. Now, we need to balance that up by selecting insulators and selecting the properties of insulators that will counteract these TOVs and the actual pollution and things like mechanical stresses. And to counteract that, we need to go and make certain that when we choose an insulator, that the dimensions of the insulator is chosen so that it can fit within the tower geometries and so on, and will actually help to counteract these stresses. The shape of the insulator, whether it is a open aerodynamic profile or a deep underrip profile, or so that all helps for different situations when it comes to the stresses. Your mechanical strength of the insulator you must select accordingly, as well as your electrical strength to be able to handle these stresses. And obviously the type of material. Now, in the old days, it was very easy because you just had porcelain or glass and maybe a bit of resin, but that's about it. But today, with the modern materials which is available, you've big selection which you can work from, and it's quite important to understand those materials. But when you balance this out, you can have a good and achieve good operating results from a high voltage insulator. And if you don't have balance and you made the wrong choice, and it's normally not you that's made the wrong choice, it could be your predecessors that's made the wrong choice, or you've been following some British standard which shouldn't have been there, and you find out at the end of the day you're sitting with a lot of failures. There's a lot of failures, so you need to now start understanding the failure mechanisms and how to counteract them and so on. But you're going to get failures, and to be able to find those failures, you need good inspection techniques, and these inspection techniques range from infrared cameras to UV cameras and all fancy equipment which you can use. And you can do it either from the ground, or you can climb the tower structure and do it. But one of the best, or you can do it with a drone. But one of the best ways to do it is with a helicopter, and with somebody that's got good eyes and got good pair of binoculars and a good stabilized pair of binoculars and good eyes. You can find 90% of the failures which are out there. So it's very much determined by the person that does the inspection, how well the inspection is going to be done, and whether you're going to be able to determine where the failures are and what failure mechanisms are taking place. And then obviously at the end of the day, which is currently one of the biggest problems, we wrote a guide for Seagray on that, and that is the handling procedures. Handling, installation, and storage. It is where the biggest problems are coming, and I can give you a whole day's lecture just on handling procedures and so on. And by the way, all the information I'm chatting to you about today is very well documented in that link I made available. And then obviously mitigation techniques. Is that something has now failed, or something is not working well in your environment, and now you need to go and you need to get some mitigation technique. Either you're going to go for washing, or you're going to go for greasing, or you're going to go for RTV silicone rubber coating, or you're going to replace the insulator totally with a new insulator. There's different options you're going to do, but you'll have to have some mitigation to be able to get that imbalance into balance. Now, we've been talking about the insulators and so on, but just a little interesting one, okay? And I am bringing this in because normally we think that the whole scenario why we need an insulator is because there's a conductor that needs to be safely strung up there in the air and have enough clearance from the ground to be safe and to be able to operate well. And it needs insulators to suspend it. And there's a whole lot of issues because it all goes around the conductor, because that is what basically is transferring the energy from point A to point B. But the conductor, and if we think about the conductor, we really always think about P equals VI cos theta. So we always think about the current and the voltage. And we basically then also say that the energy that's transferred across this conductor, P equals VI cos theta, the conductor is the main role player. And then we would say, okay, we need to look at where the current is flowing in the conductor. So we've got the skin effect, and we normally at 50 hertz, you say that it's normally that it's about 9 millimeters, where a thickness of 9 millimeters where the is flowing. So if you've got a very large conductor, say a hippo or a bull, you find that on the inside where they now have the metal strands and so on, the current is not flowing there. It's flowing in the outer layer, which is about 9 millimeters or plus thick. And then, you know, that is now your skin effect where your current is flowing. So everybody has got this big thing, and then you've got obviously the resistance and so on of the conductor, and you've got I squared R losses and all those wonderful things. But everybody is under the impression that the current and the voltage and the conductor is how the energy is transferred from point A to the load point B. So the conductor, in everybody's view, is normally everybody's view is where the energy is transferred across from A to B. But folks, it's very interesting. The current obviously results in a magnetic field around the conductor. We all know that. And then the voltage gives us an electric field around the conductor. Now the electric field is from the surface of the conductor surrounding it, and you would find that the magnetic field H is also around the conductor, and so you find that you've got the electric and the magnetic field. The magnetic field is the resultant of the current that's there, and the electric field is there because of the voltage that is present. And those two there, right, is if you take a Poynting vector and you take a look at the energy, you would find that the energy is actually that's transferred is actually the vector product of your electric field and your magnetic field. So the energy that's transferred across here, okay, let's think about that. If the energy, okay, P equals E vector product H, okay, now what is the electric field inside a conductor? Electric field inside a conductor is normally 0. Now, if the electric field inside the conductor is 0, and that's 0, how much energy is actually transferred in the conductor itself? 0. The energy is all transferred around the conductor in the air, just under the speed of light, or very close to the speed of light. The energy is transferred in the form of an electromagnetic wave. So what is the conductor? The conductor is a waveguide. That's all. I mean, looking at replacing the conductor with a pulsed laser, where the pulsed laser is basically the current level in the pulsed laser is in the microamp level, and the voltage then applied to the laser surface or to the laser tube surface is then in the order of megavolts. So I can still get energy transfer along that pulsed laser. The Japanese has done that. The Germans, the Russians have experimented and proved that. So, folks, the conductor is nothing else than actually a waveguide and the electromagnetic wave generator. The energy is transferred around the conductor. When you start looking at it from that perspective, you would find that it gives you a different ideas of how to transfer energy. And this can make you start thinking about having a transmission network out in outer space, and you can transfer energies from different outer space stations to one another by pulse laser, and you can transfer it down through a portal to Earth onto the different continents, and you can basically then have an outer space transmission network. Okay, you're not believing me, right? Maybe, maybe not, but let's think about it in this way. Here's a transformer. Here's the one winding. Here's the other winding. There's no physical connection between the two. How is the energy transferred from this winding to that winding? All right, there you got it, eh? Conductorless. It is done through electromagnetic coupling, okay? So in between, yeah, that I mean, it's actually a form of wireless energy transfer, but wireless in the sense that it's not coupled to one another. But the transformer proves the point that the energy is actually not transferred in the conductor itself. The conductors are actually electromagnetic wave generators, and it's basically transferred, making use of electromagnetic basic theories. Okay, now let's get back to insulators. We've now played enough around conductors, and we're not interested in conductors because we want insulators. Now, there are quite a lot of insulators available. The first one that ever came out was by Looms, and it's an excellent book. Even for its age, it's still doing extremely well, and it's a very good reference book. And then after that came out a book from EPRI, which is the transmission line reference book, and in there there's a very nice big chapter which is on high voltage insulators, mostly on ceramic insulators, but there's also with the upgrade they did a little bit on composite. And then Ravi Guru and our Ed Cherney and our Jeff Birmingham brought out their book, and this is their book. Very nice. I know Ravi very good, and Ed as well, and Jeff. The first course that was presented with this book was in Arizona State University, and I attended. Very interesting. Also, a bit more practical book, not bad. Then came out our book, The Practical Guide to Outdoor High Voltage Insulators, and the co-authors are Roy Macy and Dr. Claude Terrell. Claude is a brilliant researcher, and Roy is a very brilliant practical guide. So when we wrote the book, there was the optimist, the pessimist, and the realist. Now, I'm the optimist, and Roy is the pessimist, and Claude was the realist. Then there was a book that was brought out by the insulator punk, Frank Schmucki and Constantina. Now, that was brought out on silicon composite insulators. Very technical book, but worthwhile. And then also there was one that was brought out on insulators for icing and polluted by Mazot. Very good book, and you can definitely have a read on it. But also you find that not so. It's a lot of books are not so practical, you know. And then EPRI brought out their insulator reference book called the Velvet or something book. But you find there's a lot of books available. So these are the classical books available, and there's obviously a magazine available, the Insulator News and Market Report by Marvin Zimmerman. And I remember going to Brazil to do a presentation at Sao Paulo for the INMR, and yeah, my wife came back home and she had a topaz which cost me quite a bit of money. I'm still paying off on that lot, but anyhow. Now, if you take a look here, you'll see that there are different guides available. And this is just from Seagray, and you can see that there's a lot of guides on that Coagula put together. If you're writing an MSc on insulators, then normally it's very good for you to get all these guides and use them for background and so on. And you can see that there's one for AC and one for DC, and then there was all the pollution information and all the testing and the current review of the current knowledge. Very good basic guides to get you going. Then there's the IC guides. There's the old IC 815, and this now we active on those work groups. We compiled 4 documents now, which is making it even more complex for you to do insulator selection. I do a whole course and busy writing a book on the optimum selection of outdoor high voltage insulators, and it's basically tells you how to use these 4 guides to do your selection. You now really need to know what you're talking about to do a proper insulator selection. This guide here was very simplistic, and people followed it for since the 80s. You'll see it was, I think it was published in 1980 or something, and it was used since then, but we had to change it, and there were quite some big changes that took place, major changes actually. Then we're going to be working today from our book, and you'll find that in our book, we basically have chapters that cover different aspects of outdoor insulators and the practical selection and all the different aspects surrounding it. Even the mechanical components and all is taken up in the book. I've made this book available for you. You can download it, use it, share it, do what you want to. And there you'll find that it makes good reading in the bath, you know, so maybe print it out if you want to. But if you start looking at an insulator and an insulator's design, and we say that is the core, that is the real core of what it's all about, is the insulator's design. And we now go and take a look. If you want to design this insulator, what must you all look at? And what plays the influence on that insulator's design? And then further, where in the book must I go and take a look for it? So for instance, if you want to take a look at the insulator's length, okay, which is normally determined or governed by the structure type, okay, and that structure type would normally help determine the length, but the length, okay, you could go and take a look at chapter 3, and there's everything about looking at the length, but the length is also determined by the system voltage. So depending on the system voltage, actual length of the insulator is selected, and depending on the structure type, okay, the length of the insulator is selected. So that the structure type and the system voltage determines the length of the insulator, and you can go and read about it in chapter 3. You see now how to use this chart. Okay, so let's take a look. We go through this chart and have a quiz. Overhead line characteristics. Okay, normally you'll then find there's a structure type you're going to select, and with that structure type, the structure type is going to actually determine the mechanical strength of the insulator, which is in chapter 6. There's a whole chapter on the strength. And then the structure type is going to also determine the type insulator. Is it going to be a long rod insulator? Is it going to be a post insulator? Or what type of insulator is it going to be? And then that normally influences the length of the insulator. Now the system voltage. The system voltage will now determine the length of the insulator. That's in chapter 3, as we said. And the system voltage is going to determine the electrical properties which you want from the insulator. So that's also in chapter 3. See, so this here is basically setting up the length of the insulator, the type of the insulator, what mechanical properties you need, and what electrical properties you need. So the type of structure you need, system voltage will be driving those different parameters, and there you can go and see in what chapter to go and read about how to determine that. Now, this insulator, okay, is not sitting out or sitting in a lab which is pristine. This insulator is sitting out there in the environment, and the environment has a very large effect on the insulator. Actually, to be quite honest, the environment can reduce the insulation capabilities by 85, 90%. So you find that the environment can have a significant effect on the insulator performance. So let's take a look at what environmental characteristics, okay, will influence this insulator design, and what parameters of that insulator's design is actually influenced by these different environments. Well, if we look at wind and ice loading, you can get ice loading up to over a meter in diameter on a conductor. Can you imagine what it's going to do to the catenary? Can you imagine what it's going to have an effect on what weight this insulator must be able to handle? So you will find that the ice will influence the mechanical strength of the insulator, and we've got a whole section of that in chapter 6. And wind loading. So now you've got these winds. I mean, we've got winds that go up to 120 kilometers per hour. When you open up your mouth, you lose your piles. The wind is so strong. So what happens is that wind can put a significant load on your insulator. So you need to look at the mechanical strength. So wind and ice has got a very big influence on mechanical strength. Your wind loading also with the swing of your conductor, the weight, you know, whether you need to weight down your conductor at the insulator to prevent it from flying. You know, there's a whole lot of different aspects you need to look at. Then obviously we've got the other thing, which is pollution. And this is really what today is all about, is really the pollution side of things. Now, your pollution, right, will determine what creepage you need, what length of insulation you need. Then it's going to determine the profile. Do you want open profile so that the pollution can't get stuck onto the insulator and just like the wind just takes it past? Or do you want deep under profiles for the fog and so on, so that you try and keep protected areas down below? And then further, you're looking at it from that perspective, the material, because remember that today we don't just have inert materials like porcelain and glass, which don't interact with the pollution, and these materials really play no big role. Today we have materials that do interact with the pollution layer, and they do transfer properties to the pollution layer, or they absorb the pollution layer, which has a significant effect on the pollution performance of the actual insulator. Then obviously we've got a big problem, and I don't know whether in Brazil it's the same big problem, but yeah, we've got a big problem with vandalism. I know in America they've got super problems with vandalism because these guys walk around with cannons trying to shoot at everything that opens and closes, or anything that shines needs to be shot. I know of a case where they shot down a whole wooden tower structure, and that was quite only the Americans, eh? But anyhow, vandalism in our case, it's more with the glass cap and pin disc insulators, or with the stacked glass type posts, which we used a few decades back in our substations and so on. It is very satisfying for somebody to see a glass disc shatter and explode, and so they like to shoot at it or throw it with stones and so on. So vandalism is an issue. And last but not least is lightning. And lightning will determine the class of insulator you need to use, and also at the same time, lightning will determine your electrical properties of the insulator. Now, when you take a look at this, and you look at this very, very interesting little dart board we got here, we can play darts with it and throw darts at it and so on. But when you look at it, the insulators and all the different parameters, which basically it's all here. And this here is basically a summary of the book, what's in the book when it comes to insulated. And you'll find if you use this, you can very nicely get yourselves going on starting to acquire skills on high voltage insulators. Now, if we take a look, it's a very busy slide, but don't worry, relax. I'll take you through it quite easily. We've got different types of insulators which are determined by the different voltage levels, and which is normally also determined by how technology has grown over the history of insulators. I normally do a complete 1.5 hour lecture just on the history of insulators. So I'm going to be speeding through this fairly quickly. But we've got the pin type insulators, which is basically a metal pin. And then the metal pin has got lead around the thread. And then you've got either a porcelain or a glass or a resin, which then screws onto this pin. And this insulator that screws onto the pin is then made from a very good insulating material with good shed profiles on, and then normally has a coupling point at the top, which you can rest the conductor in and then basically wrap lock tie it onto it. These pin insulators are normally very prone to high lightning areas. So you normally find that you get a lot of puncturing on them, but I'm not going to go into that too much. Then the disc insulators could either be porcelain or glass, and that's where you have a glass disc, which is basically been made in the factory from a glob of glass, which is then pressed in between two shaping presses, and then out comes this disc. And this disc has then got a high tension on the surface, which makes it quite strong. When you break the disc, it shatters like a windscreen because it's tempered glass. And then you find that on this disc, they put a cap with cement at the top, and they put a pin with cement at the bottom, and it sets. And then this cap and pin disc insulator is formed. And this disc insulator, you would find mechanically, you can't pull out the pin because it pushes towards the side, and then basically the forces work against one another that keeps the pin in. And you normally find that it's normally either a tongue or clevis or a ball or socket. So it depends on the type of end fittings which are used. Now, we also have long rod insulators, and they're normally made from porcelain. We also got the line posts and so on, but it's normally from porcelain or from composite. We have the resins like the cycloaliphatic resin. But to be quite honest, I don't really promote the resins too much, as we know they're prone to hydrolysis. But that's also a whole section on just materials which we can deal with if you want to later. So the long rod insulators, we also got the porcelain post insulators, resin insulators, and then the composite line post insulators, horizontal, vertical, and then here's a little tri-arm type of composite. Very nice little design for up to 66 kV. Very nice. But let's take a look at the materials which these insulators are manufactured from. Now, you normally find that your insulating material in today's era is either a ceramic or a polymeric. And when it's a ceramic, it's either a porcelain or a glass. And this porcelain or glass is inert, and it doesn't interact with the pollution layer. And so you find that when you get pollution on the porcelain or glass, you've got the pollution on the porcelain or glass, and nothing interacts between the pollution and the porcelain or glass. With a polymeric, we've got active materials. They interact with the pollution layer. Now you can either get ones which have got hydrophobicity transfer. Now, hydrophobicity is where you have low molecular weight silicons migrating into the pollution layer. Oh my goodness, I'm telling you too much. It's something that goes and creeps up into the pollution and makes it that it doesn't dissolve, okay? Or prohibits it from dissolving. And so when the water comes onto it, runs off the surface like a duck's back, okay? Water on a duck's back. So that is where you got hydrophobic materials. It's got a phobic against water. It's got a good hydrophobicity function, but it also transfers that hydrophobicity into the pollution layer. Then you've got non-hydrophobicity transfer materials, which is hydrophilic, like your EPDMs, ethylene, propylene, diene monomer, your cycloaliphatics, your ESPs, your alkerins, your EVAs. They're all hydrophilic. Don't worry about all the fancy words and so on, okay? You'll get to know what they all are once you start reading the book. Let's take a look quickly at the manufacturing processes. For porcelain, which has been done for decades, porcelain, they use clay, alumina, feldspar, And they take this whole lot and they mix and grind it into a powder. Then it goes and it is sent through a magnet, and all metallic little particles are taken out. And then it goes to a big filter where they got these big filter bags, and then it's pressed through the filter where all the water is pressed out. And then that is like a soft clay, and then that goes into a big, like a sausage extruder, where you then throw all this clay in, and then it's pushed and pushed and pushed up against one another with an Archimedes spiral, and out comes this pug, which is this big sausage coming out on the other side. Then they take the sausage and they put it onto racks, and they put little metal electrodes on it, and on the metal electrodes they put little salt rags, and then they put a current through it and they dry it. And then it becomes like leather, goes into a leather state. And then in that leather state, they put it onto a big lathe, and then they machine it into the right shape. But as you can see from the picture, as we're going along, this thing is getting smaller and smaller and thinner, because as the moisture gets out of it, the actual clay is shrinking and shrinking. You can imagine now when you have to design this, you have to really know what you're doing. Finally, you sit with the insulator that it's now going into the oven and you dry it. Then you come out and you put a liquid glazing on it, and then it goes into for final firing. And in the final firing, then this thing hardens up and gets its mechanical strength, and it's very, very, very strong mechanically, and actually inert and is non-porous. The old first generation of porcelains had a porosity issue, where that when you broke off the actual glazing, you would get moisture ingress or problems. But that is stuff from 100 years back. You would find that your modern porcelains are fully vitrified. They've got no issues with moisture ingress. So when they chip, you don't have to now go and get glycol and then suddenly go and paint them with glycol. It's not an issue. Then they put on the end fittings, and the end fittings, they normally put a little lead washer at the bottom. They put the fitting down, they put the actual conical shaped end piece of the porcelain into it. And then what they do is they put lead and antimony, which they mix together in a certain ratio, and they pour it in. They used to use sulfur cement, but the sulfur cement normally ignites when there's leakage current activities with dry band discharges. It ignites the sulfur cement, which then burns out, and you've got big issues. I don't want to tell you too much about the rest because it will take me too long. Now, going to a composite insulator, there we start off fiber reinforced. It's a fiber reinforced rod. So we take these fine single thread glass threads which come on a roll, and there are hundreds of these rolls placed onto a rack, and then all these little fibers are taken through a grit which shapes them into a certain pattern, and then they're taken through a resin, and they pull through a resin and hardener bath, and then they pull through a protruder, and they are formed into a rod. And then this rod, as it pulls through this rod, you will find that it basically starts to cure the rod, and the rod then becomes this long fiber reinforced rod. And this rod, you can get today acid resistant rods, and with acid resistant resins, and all the issues surrounding them have all been sorted out. Now, in this manufacturing process now, they take this rod, they treat it with a bonding agent, and then it is a sheath is protruded onto it, at least 3 millimeters thick. And this sheath is a silicone rubber sheath, a HTV silicone rubber sheath, and it's high temperature vulcanized. So it high temperature vulcanizes as it pulls it through, and it's like a cable getting a sheath on it that forms this rod. And then once you've got this rod, they separately injection mold the sheds, and then they got a special machine where they stack the sheds into the right order into this, and then they push the rod right through the center, and then you've got this this insulator with a fiber reinforced core and the sheath and the sheds, and then they vulcanize the sheds on, clean the ends, and then they crimp the end fittings on. Now, the crimping of the end fitting is quite crucial. If you have only a 3-jaw crimp or a 4-jaw crimp is not. You need to roll crimp it. But that there's also a whole story on its own. So I'm going to continue down the line here. Basic overhead line insulators. Yeah, you can see the long rods and you can see the posts and oh yeah, and using a capped post for distribution systems are far better than using one with an insert. Ignore the insert ones. They were made by accident. Here is your pin types, your cap and pin discs, and then the different profiles, normal profiles, alternating shed profiles, under rib shed profiles, and so on. Substation insulators, yeah, you can see it's got a nice shapy curve, you know. Maybe it's you know, like a Marilyn Monroe insulator if I take a look at the shape. If you look at the different type of insulators you get in a substation, you'll see they're mostly posts or equipment, and yeah, you can see it on breakers. And I think the one guy that came up with said it's a Dolly Parton insulator, but anyhow. Now, the parameters on insulators which you need to very clearly understand, the measurements you need to understand before you can do insulator selection is that your connecting length. Now, that is from the hardware where it interacts with the tower to the hardware where it interacts with the conductor bundle and the conductor bundle's yoke and geometry there. Now, that distance from that ball to this Y clevis, you find that from that distance from there to there is your connecting length. And that normally influences your clearance to ground. So that is one parameter. Then you find that your dry arcing distance is the shortest distance you can take a piece of rope that does not stretch from the dead end side through the air over the sheds, right, to the closest end metalwork. Now, if there was a corona ring, it will be there. If there's no corona ring, it will be here. And that is the distance, your dry arcing distance. And that normally influences your impulse performance. And then when we start looking and we talk about insulation length, that is the length where the metal wear here is actually at its end, and where the metal wear here is at its end, the insulation in between is called the insulation length. And that is normally coupled to your pollution performance of the insulator. And then last but not least is something called creepage distance. And obviously that influences your pollution performance quite significantly. But the creepage distance is the shortest distance where you go from metal to metal over the surface of the insulator. So here you can see walking over the surface of the insulator, and the ant walking over the surface taking a shortest distance would be your creepage distance. And if we go on to confuse things and make things quite interesting, is that they brought in something new, which is called unified specific creepage distance, where we used to use specific creepage distance. Now, specific creepage distance is basically where you take that creepage distance where the lazy ant has walked over the surface, okay, and you divide it by the RMS value of the highest operating voltage across the insulator, okay. So in the old days, they used to use it where they would take your creepage distance and divide it by U max phase to phase. So normally you would have ordered a 16 millimeters per kV insulator, or a 25 millimeters, or a 31, depending on your pollution level in your area. Nowadays, that same value equates to a unified specific creepage distance where you use U max phase. So with 31 millimeters per kV, making use of the old specific creepage distance definition is 31. Now with the new unified specific creepage distance definition, it's 53,7. So you must be very careful when you specify in your specs. My suggestion is rather just specify the creepage distance and say it's so many millimeters, what specific creepage or unified specific creepage distance you want, because that could be confusing in your selection days of today. If we go on, we've got something which is called the puncture distance, and the insulator class is determined by this puncture distance. Now for a class A type insulator, you find that the puncture distance, now this is this red line here, okay, is larger than 50% of your arcing distance. So if this is larger than 50% of that, it's a class A. If it's smaller than 50% of that, then it's a class B. So you can see class B is a type of insulator which could be very prone to puncturing. And it would rather puncture than flash over the surface. Yeah, it would rather flash over the surface than puncture. And that's a difference between class A and class B insulators. Now, when you start looking at how your insulation length, now remember your insulation length is the distance from that metal point there to that metal point there, which determines your basic insulation level, okay? Now, what would happen is that you cannot make this too long. And you will then have a problem with clearance, and you need to look at your line sag. And also at the same time, you need to take a look at the amount of swing which you have. So you need to take in consideration clearances with swing. So you can't make this too long. Make this too long, you've got a swing problem. Make this too long, you've got a clearance problem. And that has got to do with line sag. So you can see what the influence is of your insulation length. Now, when we start looking at selecting insulators from and see whether pollution is a big issue or whether what parameter plays a big issue. Now, a study that was done in Seagray, which we were all very, very part of, came up with these curves. And in these curves, you'll see that the green is what insulation distance you need for different pollution levels at different voltage levels, and what insulation length you need for switching and what insulation length you need for lighting. Now, if you take a look at AC and compare it with DC, the big issue here you can see that if we're looking at 400 kV AC, 400 kV AC, okay, let's see, all right, if we look at 400 kV AC, you would find that in this case, the one that really dominates the insulation distance, the one that plays a big effect on the insulation distance is switching and pollution. So switching and pollution is actually switching and pollution, but the pollution only when it's heavy or very heavy. Very heavy. So heavy pollution and switching has got the same type of requirement for insulation length. But you find that when you've got very heavy pollution, then that starts dominating. Let's take a look here. If you take a 400 kV line under DC, okay? Now, under DC, we see, oh my goodness, the big role player is pollution. Light pollution already drives a very large insulation distance. Look what happens when you go to heavy. So the most dominant role player for DC is pollution. Pollution is your major dominant role player for DC. When you come to AC, you would find that it's normally switching plays a role for your insulation distance. But then when you go to heavy, very heavy pollution, that starts dominating the whole situation as well. Very important to get that feeling what the effect of pollution is for DC. Then when we take a look at the reason why, you find that when you look at the pollution accumulation of the ratio of DC to AC, and you look at the accumulation of pollution, you would see that there's far more pollution that accumulates on DC than AC, and it's got to do with your electrostatic forces drawing the actual pollution in onto the DC insulator. Then further, also with the flashover phenomena, you find that with AC it tends to follow the surface, whilst DC it tends to jump across sheds, ignoring that creepage distance then. So this definitely can give you an idea of the effect or the differences between AC and DC and the effect of the pollution catch on these differences. Now, normally when you want to select your insulation, you find that up to a certain level, you will only take lighting impulses for short gaps. And then when you go to the longer gaps, you start taking in your switching, and you find that this is all in the IEC standards 60071 part one. And you can this will help you to determine your lightning and your switching and your AC normal standard AC voltage levels. And here is the curves for a standard glass disc for wet power frequency, dry power frequency, wet switching impulse, and dry lightning impulse. And so you can see this is just to give you an idea of when the actual wet switching starts playing a role. And here it is for lower voltage levels, looking at from 22 to 132 and getting an idea of your Umax and so on. This is like just a little design chart you can feel free to use when you're working with glass discs. Now, this year is when we start looking at power frequency pollution flashovers. This is a line which is a railway line running next to our west coast. And as you can see that this line has got quite a bit of activity on it. And this is typically a nightly event that occurs there. And some of the first generation composites that came out in the world was put onto this little railway track line. It's a Shishin-Saldanha line. It's running one of the longest trains in the world, and is exporting our iron ore out to Japan and China and so on, which I don't feel very happy about. But anyhow, that's another story. But this shows you this line trips out nightly, and it's because of very poor pollution performance. Now, normally when there's more than a third of the insulator that has got discharge activity on it, you're living on a short thread. So when a quarter of the insulator has got discharge activity on it, you would say, ooh, I must start doing something. But when there's a third of that insulator that's got discharge activity like this on it, then you start worrying and you need to do something very quickly. Now, to give you an idea of the, by the way, Sergio, is everybody still there and you guys are still awake?
Yes, of course.
Excellent. So you're all okay? I can go for it. Right.
100%.
So now if we take a look
Sorry, Professor Foss. Would you repeat, please?
Are you still all awake and I can go on?
Well, you decide. You rule.
Let's go on. I was vaccinated with a gramophone needle as a child, you know, so I can continue chatting till tomorrow morning. So you better stop me sometime or another. Okay. Okay. So
let us see.
Let's see. Here is a little insulator. And you can see here is the dead end side, here is the live side. And this insulator tells quite a bit of a story. Now, normally what happens with an insulator in clean conditions, then you find that there's a very good insulation in between here, and you find that it's normally here in the hundreds of meg ohm resistance from this side to that side, and it's got excellent insulating properties. But now what happens is you've got these little pollution particles which are driven by the wind, and they come boom, 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 punk, and they all start collecting onto this insulator surface. All over the surface, this pollution starts collecting. And the wind is the main driver of this pollution. And these wind-driven pollution particles, when they come in here, they form a little eddy, they sit in there, they start forming around the rod, because this is a shed and this is a rod and this is an alternating shed profile, large diameter, small diameter, large diameter, small diameter, alternating shed. The spacing to shed projection ratios are important and all things like that, but that you'll learn later, okay? So now what happens, all these pollution particles come on here and they pre-deposit onto the surface. And then what happens is you get in the early morning, you get some mist forming, or you get the humidity levels go beyond 75%, they go closer to 90%, then this thing forms an electrolytic layer on here, and this electrolytic layer is conductive, and that conductive electrolytic layer, now the resistance changes from hundreds of meg ohm down to maybe a meg ohm or so, and now the currents are starting to flow over the surface. Now that whole process there oh, my wife's bringing me coffee. Whoopee! I've trained her well, eh? Thanks, my dear. And so what you would find is that that electrolytic layer that there becomes conductive and the current starts flowing. Now, when the pollution is pre-deposited like that, it's called type 1 pollution. And that is pollution that builds up and then gets critically wetting and the current flows. Now, there's another type of pollution which is called type 2 pollution. I mean, one would have guessed most probably definitely not type 3 pollution, but okay, type 2 pollution. And type 2 pollution is like an instantaneous pollution event that occurs. So insulator is beautifully clean and there's no pollution there. And now suddenly a conductive fog comes in. Now fog is formed normally where you've got a particle, and around the particle the moisture condenses, and as the moisture condenses around the particle, if it's a clean particle, it's a clean fog. If it's a salt little crystal, it's a salt fog. If it's an industrial pollution particle, it's an industrial fog. So these fogs then come and they form an electrolytic layer instantaneously across the surface of this insulator. So now there was this insulator you cleaned yesterday, and now today this thing is polluted. But what is in common of both these pollution types is that they form a conducting electrolytic pollution layer over the surface, okay? So now what happens is once you've got the conducting pollution layer on the surface, the current starts flowing. Now, when the current starts flowing over the surface, you would find that it doesn't just flow over the one side, it flows around the whole insulator and flows across the surface over the whole insulator, right? Now, where's the current density the highest? The current density is the highest around this rod sheath sections here in the center. So what happens is that when you've got 500 milliamps flowing there, it's distributed over that large surface. So you're not getting localized heating, okay? When it's flowing through a narrower surface area and you've got a smaller surface area flowing through, your joule heating is higher. And then it doesn't just heat on one side, it heats right around. So what does it do? It starts drying out the pollution layer here. And as it dries out the pollution layer, we get something which we call a dry band. And that dry band now, you'll find that the earth potential transfers down to the dry band. The high voltage potential transfers up to the dry band, and you get dry band discharges and dry band sparking or arcing, depending on the current level. And then what would happen is that the resistance of this pollution layer here will determine what current is flowing through that dry band discharge. And so the current that's flowing through here is very much the driver of how close you are to arcing, because when it is dry band discharges in the form of little corona discharges and so on, the current levels are in like under a milliamp. When you start looking at dry band discharges and you're looking at sparking, corona, you'll hear that and you smell ozone, okay? And it's a sweet smell. Very nice, actually. I love it. And when you go into a substation and there's corona discharges, or under the power line, there's corona discharges when it rains because it forms little sharp droplets. I love walking around and I can get this like, I get ozonated, you know. But anyhow, it doesn't help too much for the ozone layer. But anyhow, now when we start looking at this dry band discharges, when it goes into sparking, you will hear that acoustically it will start to more go into a crackle. That type of level, you're looking at milliamps to tens of milliamps, okay? And then it will go over to hundreds of milliamps where the acoustic level will go down lower, and you will find that now you're going into that and it starts to be a little bit more stable. And that is normally in the hundreds of milliamps. And then you find you reach a point where it basically now goes into a full arc, and now you're going into amps. And then you find you go to that, and then this arc will go from the surface out into the air, and you find that it will finally lead to the full breakdown or full flashover of this insulator from live to dead end, okay? And it's all driven by your current levels, different current levels. And you'll see that here on this surface here, it is starting, this is the moisture evaporating off as it's starting to dry out the surface level. Why are these discharges yellow? Well, they're yellow because it's salt. It's a saline pollution. If they were red, there will be more industrial pollution and so on. And so that should give you a little bit of an idea of the pollution flashover process. But the pollution flashover process is very much driven by the resistance of this and what current is flowing through that resistance. Now, it's all up to Ohm's law. Now, you'll find that Ohm is basically very easy. Ohm's law is the leakage current, that is the current flowing over the surface, the leakage current, okay, is equal to the supply voltage, okay, divided by the resistance. There you can see some dry bands. This is on an insulator. I took the photo with a normal standard camera with 1000 ASA film with a 3-minute exposure and a red flashlight. Then you can beautifully see the actual discharge activity. This was on a post insulator I tested at one of my test stations. Now, you find that the current here, okay, is determined by the resistance of this. Now, in your system, this system voltage is normally fixed. It's not something you're going to be changing, okay? So you need to look at this resistance. Now, what is that resistance? That resistance is the big role player. That resistance determines everything that's going to happen on a flashover process on this insulator from pollution perspective. That resistance R is equal to rho, the resistivity of the pollution layer, times the length. Now, what is the length? That's the creepage distance, eh? Divide by the cross-sectional area available for current flow. So yeah, you got a porcelain rod in the center, the area around it available for pollution flow, and then current flow, and then yeah, you got your length L, which is your creepage distance. So if you got your pollution plus your moisture, conductive electrolyte, that would then the area will, if you make the area, change the area or change any of these, you change that. Just as interest, if you got a insulator that's polluted, that pollution only reduces the lightning impulse performance by about 10%. Switching, because it's there for a longer period of time, it's about 50% reduction in the level, but you can see here for pollution, for AC and DC, big problems, okay? If we go on and we take a look at this R equals rho L over A, well, if we want to make R bigger, we must make L bigger. So we say instead of using for light 16, we now use a very heavy, that's 31. So the creepage will go up quite high. Make that big, that becomes big. That's why you choose different creepage distances. Now, when we start looking at the cross-sectional area, the area available for current flow, well, if this is a ceramic insulator and it's got a pollution layer of a certain thickness, which will now determine the area available for current flow, it's philic, it wets out totally. We use that as a reference, okay? Now with a silicone rubber insulator, you've got these low molecular weight silicons migrating, the stuff migrating into the pollution layer. Now, as it migrates into the pollution layer, that doesn't dissolve, that doesn't contribute to the actual current flow or area available anymore. So now the area available is smaller, that becomes smaller, that becomes bigger. Ah, cool, that's why silicon works, okay? Now it transfers all the way through the pollution layer to the surface of the pollution, and now it can't wet. Well, what is the area available now? Available for current flow? Whew, it's about nothing. When that tends to nothing, that tends to infinity, so that becomes very high. So you see, that is why silicone rubber insulators work so well. You can see here's the water drop sitting on the, and the electrolyte is not forming. No electrolyte, low area available for current flow, big improvement in performance. So your resistance goes up, current resistance goes up, current comes down, you are happy chappy. Now, if you were sitting with a thick layer of cement, this area now, okay, becomes very large. And what happens to the resistance becomes very low. That's why cement pollution becomes such a big thing. Or where you've had big volcanoes and so on. Now, you see other materials interact not positively like the silicones here, but negatively to the pollution. Your ethylene propylene diene monomer and enhanced silicon polymer, that silicon enhancement's a lot of, okay, I'd rather not say it, it's being recorded. But you find what happens is that with the EPDMs and so on, there is a tertiary, there's a weak spot in the actual structure of the polymer, and they always crack. you can take an EPDM or an ESP and they will start to form a white powder on them. And when you start looking at them with a magnifying glass, you find they crack. So now what happens is the pollution now goes into the surface of the material, and now you've got a larger area available for current flow than with ceramic, and they perform worse than the ceramics. Yeah, you can see this is the data we got on silicon rubber, EPDM porcelain, coated porcelain, cycloallophatics, and resistive glazed insulators. Resistive glazed insulators work excellently, but they're not so good for a cold switch on, and that's when you get your flashover problems. But you can see when you take a look at your levels here, you'll see that your silicons and your coated silicons are doing very well, and your cycloallophatics are really poor. And you can see your porcelains and your EPDMs. You can see that at times the EPDMs are worse, and it's because of this phenomena which we're seeing here. Now, Verma came up with a wonderful theory called the critical flashover current theory. And Verma came up and he said, right, the maximum peak value of the current 1 half cycle before flashover. So they say, he says, okay, and he did this with a lot of measurements, okay? He came up with a lot of empirical measurements and came up with this empirical formula based on those measurements. He said, right, the peak value of the maximum before flashover is equal to the specific creepage distance in millimeters per kV divided by 15,32 the whole lot squared. And then myself and Dr. Holzhausen, especially Dr. Holzhausen, came up with and said, you better take action when the peak value is a quarter of that value. Okay. And so when you're monitoring the leakage current in your network, and you've got a 25 millimeters per kV insulator, you will get flashover at 2,7 amps. If you measure 2,7 amps on that, it's already too late. It's already flashed. You need to take action when it becomes 0.7 amps, 700 milliamps. Okay. Well, to be quite honest, if you were walking underneath those insulators with 700 milliamp levels of leakage current on it, you will have to change your underpants a few times before you reach the end of the line. But this is the theory from Verma and Holzhausen and myself. And we use this in our system when we monitor the leakage currents on different insulators and so on, and we then determine what is the risks associated with that. And obviously the profile of the insulator, and you guys can go and take a look at that. We prefer open aerodynamic profiles. These are little drip lips. They shouldn't be there anymore. These under rip profiles we don't really support in our country. But it's not to say you guys can't. It's all got to do with he who measures knows. So if you look at your data and look at your measurements and look at your line performance, you can determine from that. And obviously, as I said to you, get these voltage transfers. And this is something you need to be careful with when you're replacing shattered glass discs. Here I put up in the lab 16 glass disc string with 2 glass dry discs, and the rest was likely wetted and polluted. And you can see that the string basically then flashed over the 2 discs on the earth side. So when you replace a broken disc on a string, rather replace the whole string than just the disc, or clean the whole string that are all equally the same. Here to give you an idea of fields, here is that little insulator I showed you. Here's the live side, there's the dead end side, and it's fully polluted from live to dead end. And this is a clean one, sorry, this is a clean one. And the clean one, you can see the stresses are sitting here at the actual hardware. And yeah, on this one, this one is evenly polluted from live to dead end. And you can see that the actual stresses are now sitting in the areas of smallest curvature, which is the shed tips. And yeah, you can see this is what I took with the Corona camera I designed. I designed the world's first daylight Corona camera along with a CSR. And these were some of the results of the older camera we designed, the night camera. And then if we now got a dry band area, which we created in the center, you can see that the voltage potential goes up here and the earth potential comes down, and all the stresses are sitting here in the middle. This here is on an insulator which I had up in one of my test stations, showing exactly that. And you can see the phenomena. Here we're looking at other type of stuff which you could be looking at finding on it. We've got the corona issue. This is a 132 kV insulator with no corona ring, very bad. We've got a lot of pollution due to grad E forces and also a lot of degradation on the sheath in this area. The sparking issue, the arcing issue. You must use the right type of end fittings. If you use a incorrect end fitting, that end fitting will just melt away and evaporate. After a power arc on a silicon rubber insulator, it normally becomes super hydrophobic because the silicon chains break up into small little chains, which then become available and makes it super hydrophobic. On porcelains, obviously, you need arc diverters because you don't have arcing arc diverters. The thermal shock on the porcelain will break the porcelain and you get a line drop. Obviously, the puncturing issue and then your dry band activity, you can see here with the camera where we saw the dry band, and then here you can see the physical dry band. This normally generates a lot of ozone, acids, strong UVC levels, and degrades the polymer in here just because of the actual dry band discharge activity that's there. And I think at that point, let's take a 5-minute coffee break. If you want to go drink beer, but you better slosh it down pretty quickly because we only got 5 minutes, and I would be happy if you can be back in the next 5 minutes, please.
Okay, Professor Wallace.
Okay. Thank you, Professor.
Thank you.
Right, folks, are we all back from our beer or coffee break?
Yes.
Yes.
Yes, we are here.
Yes, I am here.
Good. I'm very pleased to hear that, and you all are still awake. That's excellent. So I've not put you to sleep yet. I must say I had a good coffee myself, and my student, Barent, has phoned me and he said to me, Wallace, aren't you going too fast for these guys? You know, you must remember they are not English. I said, well, you know, they're Portuguese. They can understand anything very quickly. So I'm certain it's not a problem. Sergio, is it still all right? Right, you know.
Yes, I'm still alive.
I thought maybe what I'm going to do is to maybe go back to, you know, seeing that Barent has phoned me and is so worried about it. I'm going to go back and maybe go back to you know, the basics and go back to basic electricity 101, you know, maybe start from there. So I'm going to show you something. So if you've got children and you want to explain to them basic electricity, okay, this is one of most probably as a system I developed and which I use when I lecture to small children, which is in pre-primary school and primary school, to explain to them how basic electricity works. And to be quite honest, this works for you know, postgrad students as well. And it all starts now. I studied nuclear physics before I became an engineer. I actually started my career as a tradesman and then as a technician, and then I did physics, applied maths, and computer science as finally a subjects, and I did a honors in nuclear physics. And what had happened is that I start looking at things a little bit different when it comes to basic electricity, and I go back to the atomic level of things. And actually, it's so simple that we should start our children off with it from the beginning. And so if we start with the electron, now we know the electron has got mass, and we know the electron has got a negative charge. So it's got a negative charge and it's got mass. And so this electron, the electron, you also got something called a positron, which is the opposite of an electron, which has got a positive charge. And so for every action, there's an opposite reaction. For every something that exists, there's an opposite thing that exists. But don't go and worry about all this fancy physics. Let's just look at the electron. Now, the thing is, normally when they tell you about the electron in electricity environments, they normally say to you, well, here's the electron, it's got a negative charge, and it's a charge carrier, and this electrons, which is what is flowing in the conductor, and this is what gives you your current flow. And so they might tell you about something about electron drift, and then they will say to you that these electrons are attracted by the positive and it is repelled by the negative. And then you can get an idea that when you got all these negative electric charges, that if you've got this negative electric charge, you're going to have some electric field which can be associated with this negative charge. And so you would very easily say that a positive charge and a positive charge repels one another, and a negative charge and a negative charge repels one another, and a positive charge attracts a negative charge, and a negative charge attracts a positive charge. So those little things there you can show a child very easily, and they can get an idea just by going to look at magnets, where a north and a north repel, and a south repels, and a north and a south attracts, and a south and a north attracts one another. So you can very show this physically to a child. Now, there's one thing which they never told you about the electron, and it's something also which always bothered me. I mean, we can imagine this current flowing through the conductor. There it goes, and then we can see the charge flowing and the current flowing. And from there, we can now see there's negative charge. You could see now for the negative charge, you're getting the fields and so on. But now, how does this magnetic field form around the conductor? And where does that magnetic field come from, you know? And then they say, no, but it's there, and they show it to you with iron filings and all these wonderful things. But you say, yeah, that's fine. But now, where is it coming from? The problem is that they never tell you that the electron has got spin, and that the electron has got a north pole and a south pole. Now, when you put these electrons freely into a conductor, they repel one another, okay? But then they turn and they actually form little north, south, north, south, north, south, north, south, north, south, north, south field lines. And those little field lines are then outside the conductor as well. And you can see the actual, how the field is then formed by these little magnets aligning inside the conductor. And these little magnets, as they align in the conductor, the similar repel and the opposite attract, and they get a state where they go into. So now what happens is that to form the field around the conductor, when these start moving and they become free to move, and these little magnets start attracting to one another, then cluck, 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 they form those field lines. And because they're negative in charge, they repel one another negatively, but they also attract in different directions one another, you know, attract one another with the little magnets. And so you find that it forms a type of a flow of charge with a magnetic field around it, but also a electric field around it. And that is how you basically then get this field around the conductor. But now, if this conductor is sitting there, and this conductor that's sitting there has actually now got free electrons, and it's all sitting freely there, but now how do we get them to move? That was another thing. How can you get a magnet, take the conductor and move it across a magnet, or take the magnet and move the conductor and then get these electrons to move? But this is something that's got a charge. Now, how does the magnet move this something with a charge? Because it's a little magnet as well, it's quite easy. Because now when you bring the magnet here and you move it across the conductor, you're taking these little magnets here, they will come. If that is a north pole, you got here, this little south pole will follow that north pole. And so you can get, by moving the magnet across the wire, you can get electrons moving because you're moving these little magnets with the other magnet. Now it makes sense. Eureka! I can now see what is actually getting these electrons to move. Now you see, if we fix the magnets and we now take the conductors and we spin the conductor through the magnetic field, now what happens is that we will move these little magnets, which will move the charge on the inside. We get charge movement, we get current flow, we've got a generator running. And again, in the opposite, we can explain the motor effect, everything with that. So basic electricity 101, it's all got to do that you must not think of the magnet as just a negative charge. you must think of the electron as a negative charge. You must think about it that it's got spin and it's got a little magnet, and that there you can explain to any person in very simplistic terms with very easy experiments to show it why you have the generating and motor and electromagnetic fields and so on, where it comes from. But that's now enough of basic electricity 101. So, Barend, you've now got me to explain to them the simplicity of things. So now let's get on to a case study. Now, this case study, I don't know how much time I've got, but I will, Sergio, I just want to check with you. Can I run over 4 o'clock a little bit?
Sorry?
Is that okay, Sergio, if I run over 4 o'clock a little bit?
To run what?
If I take my presentation a little bit further than 4, well, 4 o'clock my side, it will be, I think it is, what time is it your side? It will be
for
5
now it's okay.
hours.
For now it's okay.
Start 11 o'clock. Okay.
It's to be clear, now it's 20 minutes to 11.
Okay, 20 minutes to 11.
It's okay. It's okay. It's within our frame.
Okay, perfect. Thank you.
Please feel free.
Right. Now, the last thing I want to discuss or show you today is a case study. Now, yeah, I mean, I've been flooding you guys with a lot of information in the first presentation, too much for an hour. And, but, I wanted to try and share with you as much as possible. But now let's do something more practical and something nicer than just going through a lot of theories and stuff. We're looking at a case study, and this is along our west coast in South Africa. This is the coastline, which is the closest to Brazil. And there we've got a 132 kV feeder, which is supplying a zirconium, magnetite, and ilmenite mine. But I think they're also mining there. But anyhow, this line is a 132 kV feeder, and this is a line which is supposed to give the customer a firm supply, but it's only one line. Now, our wonderful management decided that they're going to promise these guys a firm supply with one line. But anyhow, we got this line, and this line has been tripping and has been giving big problems for us. And so we have to go and find out what is the root cause of these poor performance of the line. And obviously, with these guys in the mining environment, when they don't have energy for a continuous energy supply, their plants have got problems, and they can't run their systems, and they've got big losses and so on. And obviously, then they would like to recoup their funds from us as a power supplier, because we obviously went and promised them a firm supply. Now, this is the line. You can see it's a wood pole structure, 132 kV running in, and it's in a desert marine environment. So it is a fairly high polluted environment, but most of the line is running from the inland side. Let me show you. It's the line is about 74 kilometers, and it's running here inland from one of our big substations. It's running from there to a smaller substation, and then from that substation it's running down to the mining activity down here at Brandsebaai at the coast. Now, normally in this coast environment, we got salt fogs coming in quite a lot, and so we got salt fog banks moving in onto this coastline. So we do have salt fog pollution, and then obviously we got strong winds which are coming down here, and so we get a lot of pre-deposit type pollutions, but also instantaneous salt fog pollution. So pollution is an issue here. The rain normally comes here, very low rainfall. I mean, it's under 250 millimeters per year. So we don't have a lot of natural washing that is taking place here. And we get these winds coming from the coast inland and going out, in and out like this, depositing pollution from the coastline as well. And we've got a lot of sands, because this is a very harsh environment, but very rich and wealthy in minerals and so on. So obviously a lot of mining activity. You find that on the 74 kilometers, we've got suspension structures, 409 of them, and we've got strain structures. Now, we obviously know with the suspension structures is the insulator is in a vertical position and the conductor is hanging from it. And with the strain structures, the insulator is horizontal and the conductor is actually pulling the insulator. And so it's putting strain on the insulator. The conductor is not being suspended by the insulator. So we've got 409 suspension structures and we've got 76 strain structures. Now, the specific creepage distances in millimeters per kV based on UMAX, so that was the old 815 the technique of going for it. What happens is that there is glass strain strings which are running here, and they at 26, 27, and 29 millimeters per. So they are for very heavy. You know, they actually insulated for heavy, very close to very heavy, but heavy. Okay, on the upper side of heavy. Then we've got on the suspension strings, we've got about 25 millimeters per kV, which is for heavy. So you can see that for the glass, this section here where we're running glass, which is inland, you can see that we're running at about 25 millimeters per kV, and we're doing pretty well. So the glass is sitting here in this area. Then from here onwards down towards, we're running composite long rods at 32 millimeters per kV. Now, 32 millimeters per kV is beyond the 31 millimeters per kV, which is normally recommended for very heavy. And we also got experience that at 32 millimeters per kV, we can normally find in this type of regions leakage currents below the tens of milliamps. So we've got very good composite long rod insulators up there. We also got ones which are manufactured of a hydrophobicity transfer material. So it's a silicone rubber based composite with alternating open shed profiles. That's typically what we use along the coast, is so that we don't get a lot of pollution catch. We have open and aerodynamic and alternating shed profile. So we optimize the profile and we've got good creepage distance with a hydrophobicity transfer material. So we're not really expecting pollution flash here. However, the guys in that region said, listen here, the composite insulators you used is not the blue ones. We want the blue ones because we know the blue ones are better than anything else that has been made. We want the blue ones. So I said, but listen here, guys, the ones you got here, which is now the gray ones, okay, the color doesn't make a big difference, okay? And we've tested these gray ones and the blue ones, and they both are doing excellent. And to be quite honest, in certain cases, the gray ones are doing better than the blue ones. And I said, no. You must remember, these guys don't really know too much about the insulators. They basically just used to going to the store and booking out the blue one or booking out the gray one or booking out whatever one they are available in the store. And so they want a blue one. And to re-insulate this line with the blue ones would have cost us quite a bit. And at the same time, we had to do it live line because we couldn't lose the customer. And I said no. And so they were not very happy about that. And I said, okay, that's no problem. He who measures with calibrated instruments knows. So let's go and measure and find out what is cooking there. So we went and we put something up which is called a directional dust deposit gauge. Now, if we go and take a look at the directional dust deposit gauge, a directional dust deposit gauge, directional, so it takes north, south, east, and west from which side the pollution comes from into consideration. Then it takes all the pollution and deposits it into the gauge. So the gauge is a tube with a slot on the side, and it's got a little collection bottle at the bottom. So all the pollution particles that are coming goes into this tube and falls down or sits on the tube in the inside. So when you come and you want to do your measurement every month, you go firstly and you take distilled water and you rinse down the tube in the inside. Everything comes down into this little collector at the bottom. You can see it's north, south, east, west, and so on. This is old Robbie Watson one of my sidekicks, which have been working for me close to 30 years. We've worked together for just, I think it's over 30 years now already. But anyhow, he does all measurements for me. And Robbie is an expert. He's really a stickler at it. Now, this is a standardized profile of the tube and everything. And then what we do is we then add distilled water, measure the conductivity of the water, and then from there we determine what is the pollution level. And here you can see we have different values which we can then associate with different pollution levels. We correct for our fog days and dry months with the climatic factors. So if you've got more than 20 fog days and you've got more than 3 dry months, and you're going to find that you're going to have a big correction you have to do. And then we also look at the non-soluble components, the stuff that does not necessarily conduct, but the stuff that adds to the thickness of the layer, and we also correct for that. Now, if you take a look in the area where we built a test station, we built a test station quite close to the coast at the line to determine with this test station, an online test station. Actually, that test station was used to write the C-grade 555 guide on establishing test stations along with some of my other test stations. So if you want to build pollution test stations, you can go and have a look at the C-grade guide. But coming back to this, we built a test station and we put up in this test station each and every possible insulator combination we could to prove to this group of people that are deciding that we need to re-insulate with the blue one, that it's not necessary, the blue one's not going to work. There's another problem. But anyhow, at this test station, we measured 99, a pollution index of 99. That's medium. That is not even, so that is like a kilometer from the coast, and that is typically where some flashovers were found, and that is medium. I mean, medium in a marine environment is telling me that actually it's not bad at all, okay? And then at structure 27, where there was a flashover, we put up a dust gauge and we're getting also medium. Then at another structure where we had flashover, we also measured medium. And at the substation, remember that substation where the glass stops or is light, and the substation where the glass starts is also light. So where the glass is, it's light, and where the composite is, it's medium. Now, these are insulated for heavy. These are insulated for very heavy, okay? So if you're measuring medium pollution and light pollution, I'm not expecting a pollution problem. So I show the guys the results and everything. No. We want the blue ones. If we don't get the blue ones, we're not going to throw what we call in Afrikaans a vloermoer. And I think if you translate it to English, is when a child starts stumping their feet and jumping up and down on the ground because they want a specific toy, you know. So we had quite a bit of problems with the guys. Here's the test station we built. It was quite an interesting little one because we've got a weather station, we've got dust gauges, we've got all the climatic factors. We even measured solar radiation, rain, wind speed, wind direction, temperature, humidity, and so on. And then we also got a leakage current recorder where we measured all the leakage currents on these different options. So you can see we went actually quite ridiculous with some of them, but we also went for the blue ones and the gray ones and the red ones and all funny color ones and all the different types of glass, the open aerodynamic desert profile glass and the deep ripped underfog glass. And we also did NSDD measurements on glass string. And this here is directly, the station is directly coupled to the line via a isolator link, and we use a VT as the power supply for the little logger. Now, they were happy to help me put up the test station and everything, and because they were hoping that I would find that the blue one performs and that we put up the blue one. Well, what came from this results here is that we connect these up with fuses, and these fuses are normally 750 milliamp where they blow. Not a single fuse went, and then further on the current levels, we were measuring in the tens of milliamps. We didn't reach 100 milliamps on any of them, so the tens of milliamps we reached. So it's not the pollution measurements is light and medium. The currents we're measuring on the insulators at the closest area to the problem is in the tens of milliamps. And so it's not the leakage current is not showing it, and the pollution measurements is not showing. Listen here, Wallace, I'm telling you, it's because you haven't got those blue insulators on. You need to put blue insulators on. Oh boy, okay. So then we started to analyze where the faults are. Now you see, the line runs in such a way that there's a seaside, a center phase, and then there is the inland phase on the inland sides. Now, when you take a look at the faults, you see the majority of the faults, it's not on the seaside. It's actually on the center phase. So 64% of the faults on the center phase. Now, why is 64% of the faults on the center phase? And then further, inland, it's worse than what it is on the seaside. It's not a pollution problem. There's something else. Show this to the guys. Blue insulator, please. We don't want anything else. So then I go and take a look a bit further. We take a look and we look at the statistics. Always very important to get your line statistics, because he who measures knows. And by knowing your faults and when they occur, you can start looking at other things. Now, here is the faults. There you can see the faults. Now, the faults are majority in August. Okay, here's where the majority of the faults are. Now, I would be expecting that when the fog is on its biggest, especially here, that if it was a conductive fog or a fog coming in, the Malmoki fog we call it, coming in, that conductive sea fog coming in from the coast, that my majority of faults would be sitting here if it was due to the conductive fog. It's sitting here where the fog is at its lowest. Then, if it was pre-deposit pollution problems, okay, right, then I would be expecting that when we do have our rain, that would be doing natural washing, okay, and maybe during the rain, when we get the first critical wetting, we could have the faults. But look here, it's after the rain. So it's not pre-deposit and it's not instantaneous conductive fogs. It's not pollution. Show the guys, explain it to them, give them a course on it. I want the blue insulators. If we don't get the blue insulators, we're going to continue having a problem for this customer. Okay, so now a friend of mine, Jeff Berman, he was the first guy in Florida Power and Light to come up with this whole scenario of looking at the bird excretion of bird streamer faults. Now, we've done a lot of that in South Africa, a lot of work, but it correlates very nicely with the first work that was done by Jeff. And Jeff came up with a curve where he said, well, if you've got lighting as your problem, it's here in the afternoon, around about 5 o'clock, 4 o'clock, 5 o'clock, just when everybody wants to go home. And then it's then when the lighting and the rain comes out, and then you sit with your lighting issues right there. Okay. Then, if you've got a pollution problem, it normally occurs here in the early morning hours, and especially when the sun just wants to come out, and then you get this critical wetting that occurs. So this is your classical pollution curve over here. But what Jeff found is that if you've got birds, now the bird sits, and when it excretes out this excretion, which is highly conductive and is very, very slobbery and snotty. And it forms a long, snotty, conductive like length of substance. Now, that there, when it gets into the gap, it can actually result in the gap flashing over. And then normally when it flashes over, the energy through that slobber is so high that you get very little evidence of excretion left. You might find on the surface of the insulator a little bubble that's rolled across, and you see this little streak going across, but you very seldom find anything else that where the bird excreted, you'll see some discoloration, and then you might see discoloration where the actual excretion terminated on the conductor side or so on. But normally, there's not to say that everything is under bird pollution. But this is what Jeff came up with. And I looked at this and I said, look, this is interesting. Jeff is saying that the faults are occurring here around about at 10 o'clock in the evening, 2200 hours, and here in the morning as it rises. Now, that is a very interesting thing. I wonder, because previously, remember, I looked at the month it took place in. Now I wonder if I'm going to look at what time of day these faults occurred. This is interesting. Now there's Jeff's streamer. And here is the line faults on that Juno Brunseby line. My goodness, there's a peak at about 10 and there's a peak at about 5, 6. So I take this information through to the guys. I say to them, guys, I think I've got this problem solved. This problem here is bird excretion flashover, and we must put bird guards on. What? Birds? That place is no birds, man. If you go there now, I'll take you there now, Wallace. You can drive with me down those lines. There's not a single bird in that bloody place. It's too dry, man. I said, yeah, well, I'm telling you, the statistics here is telling me, you and statistics, you bloody professors are all too clever. I'm telling you, practically us oaks in the field that know more than you, we can tell you, listen and learn. This is, you need to have a blue insulator that's got nothing to do with birds. Well, okay. So I said to them, listen here, go and do a line inspection and go and look at where the flashovers are occurring, and with emphasis on looking whether there are any bird presence on that line. So these guys go out and they do a line inspection. They come back to me. They say to me, Wallace, we told you there's no birds. There's no birds. I said, sorry, I don't believe you. I get the Liveline team. I send the Liveline team up. They go and do top pole inspection and a bucket truck. And I say, right, go and have a look for me and come back and report back. Obviously, they were in cahoots with Mr. Blue. So what happens? I come back. I say, no, there's no birds, Wallace, not a single bird. So I said, okay, I'm going to get in an independent party with a larger bird, and we're going to inspect those lines with a helicopter, and we're going to do a thorough inspection on this line. So I got an outside contractor to come in and do an inspection on the line. And there's no birds. This is a pole chanting goshawk. This is the excretion on the top of the pole. And yeah, you can see some of the excretion on the disc. Yeah, you can see the nest and the excretion. This bird is using these structures for their nesting and for perching, and they can excrete from the top of a pole to the center of the road. So they've got quite a good excretion volume and also highly conductive. So this is a goshawk which we get on that line. So now you see, Mr. Blue, there is birds. Here's the evidence. We showed you the birds. Yeah, but you know, Wallace, you know, the environment is changing. And nowadays, with these global warming things that are happening, there might be things happening. But you know what? This little thing can't shoot that far. And it's not going to, we still want blue insulators, okay? So we went up and we investigated things a little bit further. Obviously, there's birds now. So we know there's birds. So, but they still don't want to accept it. So then what they did find on the inspection is that the center phase, the jumper, is pulled in more than the outer phase jumpers. And there's less clearance between the actual center phase and Earth, okay? There's less clearance between center phase and Earth. And now what they're saying is, oh, no, Wallace, you see the problem here is an air breakdown. The problem here is an air breakdown. Because of these conductive fogs, now remember that these fogs didn't occur during the time when we had all these flashovers, okay? But now according to them, it's these fogs. And now it's a conductive fog, and it's reducing the breakdown strength of the air gap, and that is why. So they wanted me to do laboratory tests and so on, and then put a insulator sleeving over these jumpers to prevent now this conductive fog flashover. Now, unfortunately, most people in the world don't understand high voltage engineering so well, and also don't really have an idea of what influence different aspects in the gap has on its breakdown capability. Now, when you take a look at an air gap, when that air gap has got moisture in the gap, it's actually more difficult to break down than the gap without the moisture. The reason for that is that these large water molecules in the gap actually prevents the little avalanches from forming and actually absorbs the electrons and results in a higher breakdown voltage that is required for that gap instead of a lower. So moisture in the air gap actually helps the air gap not to break down more than, and it's quite an interesting one once you start understanding the breakdown mechanisms. But anyhow, so they said it's that, and if you take a look, you can see also the distance, you know, the tension insulators, the distance to ground on the tension insulator, and that for the actual jumper. Now, when we went, and I went to the old guy that designed the line, he's now unfortunately passed away, old Matt Besson. He said to me, "But Wallace, there's something big wrong with this line construction, because when I designed it, these jumpers had ample spacing and it was all good and everything was perfect and so on." Well, folks, what happened is that the poles that were delivered to site was not the correct length. The site supervisor never checked on that the poles are the correct poles. They were installed and two short poles were installed. And having installed two short poles, the actual window gap became smaller. And with the window gap that was smaller, we found that the jumpers could not be installed with their correct lengths and had to be shortened. And that is what caused that problem. But again, what happens here is that the gap is shortened, and the gap was mostly shortened in the center phase more than on the outer phases. And it was because of the fact that the window geometry was smaller because of the shorter poles that was delivered. So we now know that. Then with a finer inspection with a chopper, we found there's bird excretion on the conductors and flashover marks on the conductors. Ooh, now that is definitely bird excretion with proof of flashover marks at the excretion. And we went further and we looked on the earth wires on the tower structures. We found the signs where it terminated. We could see broken strands where it terminated on the conductor. And we could also see on the insulators and the hardware where the actual arc terminated with a flashover. We could see it on the insulator. This here is a classical power arc termination with a power arc flashover, but you could see here with the bird excretion present, and also, so this was the classical signs of bird excretion flashover on the composites. And when we started to look at comparing where the bird nests are and where the strain structures are and where the flashover positions were, where we found the flashover positions, there was a very good correlation between that. So finally, we're back with Mr. Blue, and so we now present this. We write a paper about the insulator pollution flashover problem that wasn't, and bird guards were installed, and the line performance significantly increased to the level where we at this stage not worried about the performance of the line anymore. I would not say this is the best bird guards to install, but these are bird guards. They worked quite well, and finally we managed to resolve the problem on that line. If we had to leave the guys to go ahead and re-insulate the line, they would not have improved the performance. The blue insulators would not have done its job. And it is very important for you as a utility engineer is to get your feet on the ground, get your nose out there, and go and enjoy the versatility of your career, because not only are you electrical, you're also mechanical, you're civil, you have to understand the environment, you're environmentalist, you need to understand the chemistry, the polymers, the materials, You need to understand the basic aspects of nature, like lightning. You know, it is a wonderful, wonderful, wonderful environment to play around in, and to be able to form a career where you never have to be bored, because these problems are like forensic problems. You go out there and each one is a forensic problem to solve. This is the type of food which engineers enjoy, is to be able to resolve and get solutions to a problem. And maybe to get the last word from a little bird is that undertake proper analysis and inspection to establish the actual cause of faults before taking action. And as you can see, that nice eagle flying away there, there is definitely birds, and we didn't need to have our blue insulators. Mr. Blue is now retired, and I think he's most probably happily retired and everything. But there's a lot of challenges out there for young engineers, and I think if you can get a very sound and firm high voltage background and be able to understand the fundamentals, the basics, there's no problem out there which you cannot resolve. And that brings me to the end of the presentation side of today. And so I had to go and take a look of how to say thank you in Portuguese, and I came up with, my wife is quite a linguist, and she said obrigado, you know, so I must say obrigado. And with that, I'm handing over to you, Sergio, and I'm open for questions or any discussions further, and let's take it from there.
Okay, Professor Vosloo, I'm sure you all are very well impressed with your presentation. Congratulations. Thank you very much. It has been very impressive. You gave not only a brief insight, you gave us, how can I say, a perfect view of what happens when dealing with insulators. I'm sure that from any of these slides, we could spend hours with pleasure for discussing all the news you brought to us. Thank you very much. Thank you very much. Thank you immensely. And now, perhaps you should consider one of the students to make questions. Would someone please do a question to Professor Vosloo?
Yes, Professor Vosloo. I have a question. Could you explain again why does the DC insulators tend to accumulate more pollution than the EC?
Good, thank you, Felipe.
Felipe, that's a very good question. And it's all got to do with the electric fields around the insulator. So what happens is under AC, the fields are actually then going in the one direction, and then as the voltage changes, it goes in the opposite direction. And so what you do is you've got these electric fields which are actually changing from direction, the one to the other. And as it changes from direction, it goes through, you know, points where it's now attracting the pollution, and then where it is actually pushing the pollution away, and attracting the pollution and pushing away, and so on. And in general, with time, over a long time, these grad E forces tends to slowly pull the pollution in for AC, but it takes a long time. And then you find normally here at the high voltage side, where the highest stress is, the insulator starts slowly to becoming on a composite insulator a little bit more black. If you don't have good corona rings, if you do good electric field stress arrangements, you find that the effect is less. But on AC, the pollution is basically more driven by the wind, and it's deposited by the wind, and that is the main deposition scenario. The actual electric fields, because they're alternating, has got a small effect. However, on DC, you also got the wind depositing the pollution and so on, and in very severe environments, that is the dominating factor. But when you're in an area where, if you had AC insulation, you would not find that pollution is much of a problem because it is not caught onto the surface because of the electric fields. You find that when you put a DC insulator there, because it's at one polarity, now what happens is that the pollution becomes attracted and is actually drawn to the pole. And you find that your pollution now, even if it's a light environment for AC, it becomes a heavy or a medium environment for DC because of the actual field, which is now static, which is not changing, is now drawing in the pollution, and now you get an electrostatic pollution catch. And that electrostatic pollution catch, it's like when you're going to be painting with static electricity. You're gonna put a charge on your car, and then you're gonna take your spray gun with charged particles, and then when you spray, then the particles are attracted to the car. If you had an alternating field there, then you wouldn't get the particles onto the car. You find, but with a DC insulator, those high field stresses or the field stresses that are there, because they are not alternating, they draw in more pollution. And that is why you find on DC insulators, there are more pollution accumulation. Does that help?
And that's why we should consider DC insulators with lower flashover voltage than AC?
Well, you will find that you would have to use DC insulators with a far higher creepage distance because their pollution performance is worse than for AC. So you're going to need longer, bigger insulators for DC than what you're going to need for the same voltage level for AC. Is it clear for you?
Is it clear? Thank you, Professor.
Thank you, Felipe. Any other question, please? Please do it. Please consider this chance we have to share this knowledge of Professor Vosloo. Well, Professor Vosloo, I'd like to know, well, I would have several questions to all your presentation, but in few words, what is the advantage of existing of rain? What's the role played by the rain in insulator pollution?
Well, there's two roles. You could have a negative role, and you can have a very positive role. Now, in our case, for instance, we have very long periods, especially at our power stations, where there's no rain. So now what happens is that the power station spews out, and don't think that coal power stations don't spew out pollution, they do. And so and also, by the way, don't think that coal power stations are not a nuclear risk. You can get a higher radiation level from a coal pile than what you can get working at a nuclear power station. But anyhow, so what happens is this pollution is deposited and built up and deposited and built up and deposited and built up and deposited and built up, but there's no critical wetting. So there's not even a little drizzle of rain, and there's no fog banks or nothing. There's no critical wetting. So this pollution builds up. And then one day, suddenly, the first rain comes with these big raindrops. Ploof, 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 ploof. All hell breaks loose in our power stations. And the power station bus bars, the equipment, everything starts flashing over. And then the rain continues, and then it starts washing off the pollution. And as it's rinsing off and washing off the pollution, now the risk becomes lower and lower and lower and lower until all the stuff is washed off, and then you get going. But you cannot risk that first few drops with this very extreme pollution buildup. Now, in other environments, you find that you get so much washing, like next to our coastline on our eastern coastline. Well, we get over 1,000 millimeters, 1,000 millimeters of rain per year, and for us that's a lot. For you guys, that's not so much, but for us that's a lot. And also, we get strong winds along with this rain. So what happens is continuously the insulators are rinsed and washed, with these, and it's a high rainfall area. So we got lots of washing, lot of cleaning with the rain. So there the rain is playing a very positive effect. But also at the same time, the rain and the wind can have a negative effect on our silicon greasing of the insulators, where the high wind and rain then pushes the grease away from the insulator surface towards the side. And then when the first pollution comes, then it flashes over that area because it's not hydrophobic. So you need to, you cannot say that rain is good or rain is bad, it's both. And we normally would prefer to have good natural cleaning with the rains. And so we need to understand your environment. You need to understand the pollution processes in your environment so that you can holistically look into this whole issue. Because you see, you've got different things you can do to prevent the flashovers from occurring. And by looking at those different things you can do, you will choose the one based on the environment you're in. And so, for instance, in the power stations now, we've put a RTV, a room temperature vulcanized silicon rubber coating on. It's been going for over 20 years, and we haven't had a single flashover after we put them in, because they now are transferring their hydrophobic properties to that pollution buildup during the dry months. So when the first rains come, then the rains cannot form a electrolytic layer. But what happens is because of the mechanical impact, the rain starts removing those pollution deposits slowly, and so we find that we've managed to get past that problem. In KwaZulu-Natal, along our east coast, where we got the grease that's being shifted away, we don't use silicone grease at all anymore for improving our performance. We also put a RTV silicone rubber coating on there, and those problems on that coast for the instantaneous events, because typically in the East Coast, we get temperature inversions with a sudden pollution deposition taking place, and we need a surface that can handle that. And so that surface, we now use a RTV silicone rubber coating. Actually, to be quite honest, our whole network, all our substations, most of them have been upgraded to RTV coated porcelain, and where we can, we've used composite busbar stringers, and also on our lines we start using majority hydrophobicity transfer silicone rubber materials. But okay, I've diverted a little bit away just from the rain, but hopefully that has answered your rain question, Sergio.
I see. Thank you very much. But one other question, if you allow me. Probably you have lived all this change. Maybe you have the ESCOM technology that was not so adequate to South African environment. Maybe with some how can I say, standards or practices from UK, for example, I suppose. And step by step, you could recover and consider what's necessary to South African environment. Is it true? It seems very clear for me that you have lived this transition by discovering and contributing for making correct adaptation for the materials and insulators to every area in South Africa.
Yes, the IEC standards are not relevant to all countries. And that is why it's so important that you are actively involved with both CGRA and IEC. And I'm very pleased to see that Brazil is definitely not shy to show their presence and do their thing. And it's the same from us from South Africa. As Southerners, we are all there to show these guys up north that, listen, yeah, we also do exist, and our areas are also unique and so on. Actually, be quite honest, the concept of an instantaneous pollution event originated from us down here. So it's very important that you actually don't just accept the so-called first world country information as being the gospel, you know, and saying that because they use arcing horns on transformers, we need to use arcing horns on transformers. That's the worst thing you can do, because when you put an arcing horn on a transformer and you actually chop that wave, you're putting your insulation under extreme stress. So we basically immediately said no. And And I think if your country develops a good research base, and your utilities and the government supports a sound research base, you can measure and observe and know by doing that in service and in the labs, but especially in service. Your field personnel is your ears and your hands and everything in one. And so it's very important that your field personnel understands high voltage insulation, but especially insulators. And about each and every insulator failure, we've seen this side and we've learned from it. We were the dumping ground during the times we were placed under very big restrictions. We were the dumping ground of high voltage products, and so were some of the first composites that went up in the world. The Mark Zeros went up in South Africa on a 400 kV line. The first brittle fractures occurred here. So we've learned a lot. And yes, every country has got a uniqueness to it. And I'm certain that when I start to understand what's going on in Brazil, and get a little bit of a deeper insight to the issues from a failure perspective or from a success perspective in Brazil, we can learn from that as well here in South Africa. It's a forum you're continuously learning. For instance, now the bonding problems between the rod and the sheath, and that bonding issue is now going to become part of the new IEC standards. I've got hundreds of them failing here in the field because the guys didn't listen. And it's not only a phenomenon occurring here, it's occurring worldwide, and it'll be interesting to see how many is occurring in Brazil, because what happens, your field guys tend to hide the failures, so you need to get their trust, and you need them to be excited to come and tell you about the failure. And I normally reward guys that bring me failures, so we get the most amazing failures coming in from the field. But yeah, we definitely don't just follow the British anymore. And I'm certain you guys don't just follow whatever comes from the Portuguese government anymore for years. So,
exactly.
I can see it with the labs and the infrastructure and the research papers and the work that's being done. You guys have got a very nice, strong process running in Brazil, which I think you can feel very proud of.
So, thank you so much. Very clear, very complete. Well, by now I think we are very close to the lunch time in Brazil, and maybe our students are a little bit satisfied, I'm sure. And I would like to thank you once more for your not only excellent technical presentation, but for your inspiring words in view of motivating our students to go ahead and to take their own place in this market and play an excellent role as engineer and as a master researcher. And so, Professor Foslo, thank you very much. We hope we can continue our discussions through WhatsApp and for future actions. And there are many items you mentioned that are very interesting for cooperation. For your close retirement or moving to the savage, to the jungle, and we count on you. And I'd like to thank also Baren for your presence. And please feel free to contact us if you need if you have some additional interest in some other questions and so on. And I don't know whether someone wants to give a final word, to say something to Professor Foslo, to thank him with someone.
I did, Professor Cabral. I really appreciate the practical way that the Professor Volvo explained this works, his work. I really appreciate, and the problems are very similar that we live here in Brazil because the weather is similar and the conditions are similar. So thanks a lot, Professor Vosloo.
It's absolutely my pleasure, and feel free to contact me if you have any problems you would like help with and so on. Always open for helping.
So great.
Thank you.
Okay.
Thank you very much, Professor.
My pleasure. And I hope you guys are going to have some beer with your lunch.
Oh.
Just a little bit.
We have the afternoon, Professor.
But you know, life is too short not to have good beer, eh?
Yeah, why not? Okay, thank you to you all. So we consider this as the final for this in this meeting, but I hope you may have many other meetings in the future. Okay, so have a good day, you all, and we hope you may plan a new speech of Professor Vosloo as soon as possible. Okay, so bye bye.